little bit at Zurich at some point, and then I was in an LBL in Berkeley at the kind of multidisciplinary lab, and then I was 6 years in a Swiss bank. Now I'm out of it, and we want to solve a problem which is actually addressed or was affected by every one of you, so you will see what I'm talking about. So maybe just one word where Zurich University of Applied Sciences is. It's different to the other research universities that we have in Switzerland. We're actually doing projects with industry, which means applied projects, so we cannot just dream up nice ideas and then publish papers, but we have to dream up nice ideas, publish papers, and make them relevant for industry and also for society. So this means what we do actually, it should work for a company, and it should actually have an implication. So our university is pretty young. On the other hand, it's also quite old. It was founded in 1874, quite some time ago. But since 2007, it actually changed the momentum quite a bit. So it was different universities in the area were united to the Zurich University of Applied Sciences, where now the applied research is actually focused and working with industry. What is nice, and we're very proud of it, one of our most famous lecturers was Mr. Einstein. He was teaching in Winterthur for about half a year or so. Then he was kind of kicked out, not because he was not so smart, but he didn't fulfill the very high standards of the Zurich University of Applied Sciences then back, the technicum. So I think we missed the change here for some time. So this was the introduction. Now I tell a little bit about the problem, and you will see what the whole thing is. I suppose you all remember what happened in 2007 or 2008. There's a statement from the US Secretary of Treasury, Mr. Paul Hengsen, and he said in 2008, when this famous investment bank Lehman Brothers filed for bankruptcy, he said, well, the problems have been understood, and you can very easily let Lehman Brothers go down, no problem at all. So this was this. Statement is here. What happened actually here? It was a nice statement. Was it based on facts? Maybe not. We heard during the last 1 or 2 days, we heard quite a bit of fact-based decision making. This was an example which was maybe not fact-based. There were some theories and assumptions, but no real facts. Interestingly, what was the response of the British Academy to the Queen? So they also had an important, if the Queen says something, the world listens. What did she say? So everything they said everyone did, in principle, everyone did a very good job, and the small risks are also okay. But the problem is that if you take all the risks together and if you sum them up, then it's actually not a problem. Then it's not okay. And this is exactly what actually happened here. Maybe they looked a little bit at every small one, but they didn't see, or they didn't want to see that the world is a little bit connected, and especially the financial world is extremely connected. We heard also this morning about stress tests. I think this was a talk by ZHAW, and this is exactly what is happening from time to time. That the central banks say, let's figure out how our banks are doing. Do they have still some critical assets, and how are they actually doing? And then they do these stress tests, and this is when the banks get really a little bit some work to do, because central banks from different countries say, tell me how much bad and how much junk you have in there and how much good stuff, and then they do some calculations. In the end they come back with a number and they say it's great. And this is what they're doing regularly also at the European Union level. And if you remember in 2010 there was this stress test scenario, and the outcome was that one of these Irish banks did extremely well, and the Irish government also did extremely well. 2 months afterwards, Irish government went bankrupt. Something similar happened to a bank called Dexia, which is a French-Belgian bank. Also stress test said great. One of the strongest banks in Europe. What happened? A few months afterwards, it also just tumbled, disappeared. If you see this, there's something a little bit wrong. We can fly to the moon, we can build physics detectors, we got the Nobel Prize for the Higgs boson, but these problems, I think we just let ourselves fool, and we think in terms of business, in terms of money, everything is possible. And I think it shouldn't be the case. Take a little sip here. Good weather. Good morning. So what we see here is this is a chart or a graph from the Risk Institute, from the World Economic Forum, and they actually looked at how different risks are actually connected. For instance, here this green one is climate change, and this kind of pink one, this is government failures and so on. This orange one is terrorist. This is also a very, very bad thing and we cannot really understand it. And the blue one is actually financial risks. If bank fails, if government fails and so on. And the interesting thing is this is all really connected. So if one bank fails and they are pretty big, then another one fails and then a whole country fails and maybe a whole continent fails, and we have seen what actually happened in the financial crisis. Now let's see this. These are all the risks together. This blue part is just the risks from the financial perspective. And now let's look at how all the banks are actually interacting. You see a nice graph. You see the big guys, Bank of America, Citigroup, some Swiss banks on the other side. You have Lehman Brothers, the very famous one. You have Merrill Lynch, you have AXA, French bank, and so on. And this just shows the banks. The problem is, if you take one of these big guys, they are not just one legal entity. There are maybe hundreds or even thousands. Like, let's take HSBC Germany, HSBC Singapore, and HSBC whatever. They're all in different countries and even in different regions. They are different legal entities. So this means you have many connections actually between them, and just finding out if you have a financial instrument from one of them to whom it belongs and how it's packaged is extremely difficult. So now what we're doing in our project is that we say we want to have finding a little bit out what is the state of the financial system, and analyze it in a little bit more, let's say, unified way. That not every bank does their own number crunching and comes up with a number 28, it's great, and the other one has 55 and it's even bigger. But the calculations they're doing are actually done completely differently because they have different data models and they have different approaches. So therefore we have founded this project called ACTUS. And ACTUS stands for Algorithmic Contract Types and Standards. So the idea is basically that you say, as you can model in physics, you can model a detector and you can model the particles and you have one data model maybe. And pharmaceutical companies have data models for drugs, and biologists also have their data models. In the banking world, this doesn't really exist. Since there's no need for standardization, why? I mean, it's much easier. If everything is complicated, you can sell complicated things that people don't understand, you can sell much better. So therefore, the idea is that you standardize the data model, and then when you do the stress test, when you really figure out how critical are things, that you can actually compare it, and then you can do it in a more profound way, and not doing some kind of guessing and hand waving, and everyone kind of produces their own number. So how actually the thing works is what I find interesting, especially when someone thinks about banking, everyone just thinks of high frequency trading and that's the greatest thing. Everyone builds their own algorithms, and physicists like it because they can do their math, and some others who don't understand it like it because they think they can get rich. I would say, yeah, this is nice, but I don't think you can really compete against the big bank because they have also quite a bit of computers. So everyone is kind of focusing on here, doing some market prediction and modeling maybe the counterparties and so on. But our approach goes a little bit differently. What we say is financial contracts, so these are basically the banking products. And this can be, for instance, you can have a loan, or you can have your savings account, or you can have a mortgage and so on. We say that we build one data model, so rather than everyone does it differently, we do one standardized one. And then what you can do, you can calculate different KPIs or key performance indicators. You can see what is the value, how much money actually flows in, how much goes out, what is actually the income, so you just deduct what goes out from what goes in. Then you can also calculate the liquidity. If you want to take the money out, does it take 3 months or can you get it immediately and so on. So you can do all kinds of nice calculations if you have kind of this unified data model. And how this actually works, this has been, there is some financial theory around since 2009, and this was done by some colleagues of mine, Brammertz and Reimann. One of them has his own company, a financial company, and has actually implemented this standard and has been working with financial institutions already for quite some time. You can read this up, it's kind of an interesting read. It looks at the finance perspective a little bit different. So more like, it doesn't treat the markets, it takes the markets and all this high frequency trading information takes as an input, but it focuses more on the contract modeling and that you can standardize and get the results in a unified way. So here I discussed before a little bit what kind of things you want to calculate. So basically you can calculate then if you have this, if you assume now you have a small company, a small bank, and it has so many shares and so many stocks and whatever, you want to see what is the value. And then you want to see it maybe not just for one company, but maybe for several companies. If you aggregate it, you want it maybe for a country, or even for a whole region or a continent. So the goal is really that you can have a global perspective. So here the idea is like, in weather forecasting, we can say, we calculate what is the weather for tomorrow, but we don't have something similar for finance. We cannot say, what is the risk in this country, what is the risk in this continent, or whatever. It just doesn't exist yet. Because everyone basically does their own soup. So the idea is then when you take our approach where you say, you standardize the data models, you calculate more or less in the same way, then you can use this approach in a quite nice parallel way. So you can use it for each company and maybe for countries and so on. The nice thing is, it can be parallelized pretty well. Because what you do, you say, for instance, assume you have a simple government bond. You know that it runs for 10 years, and for simplicity you assume that every year you get 1% interest rate. So you can calculate the cash flow, like after 1 year, let's say you have a government bond for, let's say, 1 million, and you have 1%. So every year you can calculate for 10 years how much cash flow you will have there. And this cash flow, you can sum up and you can evaluate this. And then you don't want to only do it for one product, but maybe you don't have just one share, but maybe you have 100. And you don't want it to have just for one customer, but for 100 customers and so on. And all the calculations you can actually do in parallel. It's all, you know that the effects of the financial contract, you also know what are the expected interest rates, for instance. And then you can calculate scenarios, simply like use Monte Carlo simulation for physics, if you will. You can do basically exactly the same calculation for cash flows of financial contracts. And this is nice from the parallel perspective because it's nicely embarrassingly in parallel. You don't need to, for calculating different scenarios, they're completely independent. So this means it's a nice, for parallel computing this is a nice and easy problem. So the problem here is not so much the calculation itself, the problem is more getting all agree on this data model, and once you have it, making all the banks actually do, not just implementing the data model, but transferring what they have from their data models to this standardized one. Here's a little bit more example of how this looks like. So assume this is a very simple, assume this is a government bond and it runs for 12 years. And in the first year you get maybe 1 million of profit, and then you get even more, and at some point it becomes smaller, and then at some point it's negative. Then you can calculate, for instance, a cumulative liquidity. So what is it worth after 10 years, after 5 years, and so on. And then you can also put it in a nice table, and you can do all kinds of charts. What you then want to do is, then you assume, okay, let's look at the major central banks in the world. Let's look, for instance, how does the US Treasury change the interest rate? Or how does the European Central Bank change the interest? Does it even go now from, what is it currently, minus 0.5% to maybe a little bit lower? So you can see if the central banks change the interest, what is the impact of all the instruments that I have, or the banking products that I have in my portfolio. So this means you change the parameter here, you change the interest rates, and then you can change what is the impact on the cash flows. So you basically run your algorithms again on all the banking products you have, use Monte Carlo simulation for each of the different scenarios, and then you come with a bunch of big cash flows that you store in a data warehouse, and you can analyze it afterwards. So this is one problem. Another one is that you say, now you have calculated it. Remember the chart that I showed you in the beginning? You have this big graph of everyone is connected, so it's not just the 10 big players in the world, the top banks maybe, but each of them has legal entities, and they split it up, and they split it even up. So you have to model it as a real graph problem. So it's like, let's assume you have 10,000 banks and you split them up, and then you have suddenly 1 million of those. So it's a big graph where you see the connections. And on the edges you calculate basically the cash flows. So it's a nice, it's a nice problem. It's a big graph, and on the edges you do basically your Monte Carlo simulations. What are now the challenges? Why do we come up with these things? As I showed you already, we are now in 2014. The theory was done like 5 years ago of this unified financial modeling. A company has been built. They have survived so far, and they're actually doing quite well. Now we're going into this step, and the question is now, why now, and why should we be, and what is actually the challenge here? And here the challenge is what we heard before, and all the time it's big data, and what I think the real challenge is, if you actually have your enterprise data warehouse, and you get all this information not just from one detector, but maybe you get it from 10 different customer systems, and there's trading system in New York, and there's trading system in Zurich, and then from Singapore. They all basically do the same thing, but they all describe it slightly differently. So it's really an integration problem, a data integration problem. First of all, to map to our data model, and then you don't want let's say if you have hundreds of these different ones, you don't want to manually maybe write your ETL process, or maybe you do it with Hadoop and do kind of a machine learning approach to discover the connections. You kind of want to have some semi-automatic approach for doing this. And this is a non-trivial problem that needs to be solved there. The other thing is to calculate actually the cash flows. I think this is more of a changeable problem. It's a typical Monte Carlo embarrassing parallel problem. So this is okay. But what you want actually, and this is actually where this open source Hadoop-based discussion actually comes into the game. We could very easily do all the calculations, store it in a big data warehouse, being it Teradata, or maybe you also can store it into Oracle or SAS or whatever, but then this is really, really expensive. And maybe you don't want to have petabytes of this data in these expensive things, but you want to have it maybe in something less expensive, but which actually scales better. So therefore here's the thing to see when we build this, how we can actually store it in this nice big data tool. What is the other challenge is that we say, okay, now we see, and the problem that we actually currently see, before we wanted to see, okay, I have maybe some investments somewhere in Russia or in the Ukraine, and currently things are happening in the Ukraine. And maybe your health insurance or your life insurance has invested in some companies there, and you maybe want to know, does it have effect on my mortgage or my life insurance? So therefore you want to simulate all these kind of scenarios. So this is one thing that, and the thing is you want to have the answers actually quickly. Not in 3 days, maybe not in a week, but the goal is here that you actually get it in a day. Or maybe even faster if you need this. Then the other thing is also that you want to, now you have stored all the cash flows in there, you want to calculate things like what is the impact on this company, what is the impact maybe on this government, on this country or whatever. And this is a little system architecture of how the whole thing looks like. So down here you have you have all these nice financial institutions that have their troves of data, all stored slightly different, but in principle, most of them doing similar things. Down here we have more or less our unified data model, and this is actually interesting. When you look at how many banking products there are around, what do you think? If you sum it up, how many do you think are there around, roughly? 50,000? 50 million? Billions? I would say it's several billions. The interesting thing is there are even hundreds of billions, if you will. But the interesting thing is you can model, or you can reduce them to like 30 different types. And one type might be, this is a government bond, and you get cash flows every year or whatever, and the other one is a stock option, and the other one is some more complex thing. So you can reduce them from several billions to about 30 different types. We've implemented about 12 already. And if we implement another 6, then we've covered more or less 80% or even 90% of all the financial products that are actually in the world. So this means you can actually, it's a tangible problem, you can reduce it from several billion to 30 different types. So you would have it here, and then these financial institutions would then need to map their data model basically to these 30 different types. And once you have it, you can load it in there, you can do your Monte Carlo simulation to calculate the cash flows, to see what is actually the impact, and you can do your stress tests and so on. And these Monte Carlo information results will then be stored in your big data system, or your Hadoop system. And then what you want to have on top, and we had yesterday a nice discussion about standardizations. If you store them now in Hadoop and you maybe want to do your analysis in Impala, or you use another big data system, and on top of it, maybe someone has their favorite BI tool, being it ZHAW or being it Oracle, whatever. If you have a standard interface, it doesn't really matter whether down there you use open source big data technology or the expensive Teradata. That's the word here. This summarizes it. What I find really interesting, I hope this actually gives you a little bit of an idea what we're trying to do here. The financial ideas are not from myself. They are basically from my colleagues who have started it for some time. What we're helping in there is actually getting it to a larger scale, so that you don't actually simulate some small amounts of financial contracts, but actually large ones. You can even go to the website. It's called the Actus project. You can play with, there's some example data in there. You can play with it. You can simulate your own bond if you want it. You can do some calculations on the small scale. You can actually do it. But now the idea is actually to do it even in the larger scale. So this actually shows this is a real nice interdisciplinary problem, because you need some people who understand the finance, the mathematics, and the economics. We also have people in the team that understand data warehousing, big data, and so on, plus also parallel programming and security. So this is kind of a nice ensemble of all kinds of problems, with the goal of hopefully making some of these fuzzy financial calculations a bit more tangible, and hopefully avoiding some of the missteps that happened in the past. Okay. Well.